Hi, it's Mr. Blightstone here with the second video for Unit 1 for Algebra 1, and in this video we're talking about sets and domains. So let's take a look. What is a set? Well, a set is a collection of elements or members, and usually the elements are grouped for some type of purpose. So here we have names of sets and one of their members. So a herd of dairy cattle, the member is a cow. A team, the member is a player. A committee, the member is a member. The U.S. Senate, which, if you're not from the U.S., it makes our laws, a senator. Class, the member is a student. A deck of cards, a member of that is a card. So a set often has different properties from those of its members. For example, a team in baseball can win the World Series. That's the biggest game in baseball, the championship game, but a player cannot. So the team can win, but the player cannot. But there's an award called the most valuable player that a player can win, but a team cannot win that award. So sets can have different properties than those of its members. So let's say how we name sets. We use braces, which are these curly Q things, and we use commas to separate the elements. And we often name the sets with letters. So let's look at an example. So if Lulu, Mike, Neil, Oscar, Paula, and Quincy are the 6 members of a committee, we could call that committee C and write that. C equals Lulu, comma, Mike, comma, Neil, comma, Oscar, comma, Paula, comma, Quincy. Now, let's say I make another set, and I call that set D. I could say D equals, and let's see here, I could put Mike in that set, and I could put Quincy in that set, and I could put Oscar in that set, and I could put Neil in that set, and I could put Paula in that set, and I could put Lulu in that set. Now, what can we say about those two different sets? Well, let's look at their elements. Let's see here. This one has Mike. Well, so does this one. This one has Quincy. Well, so does this one. This one has Oscar. So does this one. This one has Neil. Same. This one has Paula. There. And this one has Lulu. Good. Well, it appears to have the same members. They're just in a different order. So that's okay. These sets, then, because they have the same members, we can say that those sets are equal. So we can say that C equals D. Now, if I were to say, take one of these from it, like if I got rid of Neil, then they would not be equal. They would not have the same members, so they would not be equal. So the order of elements in a set doesn't matter, just like we saw. And they're equal if and only if they have the same elements. If and only if is something important we'll see a lot in algebra and geometry. If and only if. All right, let's look at some sets we've kind of seen before, sets of numbers. So these are ones we use a lot. Whole numbers. 0, 1, 2, 3, etc., etc. Some examples. 5. 16 over 2. That looks like a fraction, but it's equal to 8, so it's a whole number. 1996, 7 million. Integers are the whole numbers and their opposites. So 0, 1, -1, 2, -2. So 21 over 3, which is actually 7, so that's an integer. -17.00 just means it's 17, -17, same thing. -1000, all integers. Real numbers. The set of all numbers that can be expressed as terminating or non-terminating decimals. So if we can express it as a decimal, it's a real number. 5, 0, pi, -0.0042, 3 1/3, 0.13 repeating, square root of 2, 100,000, all of them are real numbers. Now notice that all whole numbers are also integers, and all integers are also real numbers. So then all whole numbers are also real numbers. So it kind of works like that. It's kind of interesting. We'll probably look at that later again. All right, a couple more definitions. So the domain are all the values that may be meaningfully substituted for a variable. And the solution set of an open sentence is a set of numbers from the domain that are actually solutions. So let's look at an example here. Okay, so it says graph all the solutions to x is less than 9 when the domain of x is the indicated set. Whole numbers, so this is A. So we're graphing on number lines. So x is less than 9. So 9 is not included, but less than 9. Well, let's see here. 9, no. 8 is less than 9, so we'll put a dot. 7, same. 6, good. 5, yes. 4, fine. 3, good. 2, yes. 1, fine. 0, good. -1, no, it's not a whole number. We stop. There's our answer. Integers. Well, that includes all the whole numbers. So I'm just going to quickly, I know these aren't exactly centered. Four, 3, 2, 1, 0. Now integers, we add negative numbers. Okay. Real numbers. So real numbers, anything that can be a decimal. So that means numbers that are in between even. So like, and numbers that are really close. So what we want to do is we want to make an open circle on 9 because we're going to get really, really close to 9, but we're not going to touch it. So that means the circle is open. That means we're going really close, but not touching. So move that circle a little down, a little. Sorry about this, folks. There. And you can't move the circle down, move the number line up. Okay. So we then use the whole, and we put our line there, and we try to go straight as we can. And since it's real numbers, anything less than 9, so we just keep going down to the end here. And at the end, we'll make an arrow, and then we'll color it in, we'll shade it in, like that. That is our solution set for the real numbers. Okay, so here's a problem you can try yourself. It says, graph all the solutions to x is greater than or equal to -3 for the given domain. So pause the video, see what you can't do, and then hit play again to see if you got it right. Okay, so if you're back, then we're looking for A, the integers. Remember, integers are the numbers, the whole numbers and their opposites. And we want greater than x equals -3. Greater than or equal to, excuse me. So, -3, is that greater than -3? No, but is it equal to? Yes. All right, so let's make it a little bigger than that. Now, which direction do we go? Greater, well, that's getting smaller. Going to the left is always getting smaller, so we go to the right. So we put a dot here. And there, and there, and there. 3, 4, 5, 6, 7, 8, 9, 10, and then we would draw our arrow and fill it in. All right, real numbers. Real numbers, similar to the way we did the last one. Since it's greater than or equal to -3, we want our circle to be closed. So we're going to draw kind of a big circle there. Make it even bigger so we know. And then our line all the way down to the end. Make your arrow shaded in. There we go. So that's the solution to x greater than -3 for those given domains. All right. So when we go into the real world, real problems, we have to decide what domain might make sense for a situation. So here's the example. It says, let x be the number of people at a meeting. Name a reasonable domain for x. Assume there are more than 15 people at the meeting and write an algebraic sentence using x, and then graph the solution set in part B. So let's start with part A. But let's use a thinner marker. A. Okay, a reasonable domain. Well, real numbers won't work. Why? Because you can't have a decimal of a person. You can't have 0.1 people. So real numbers are out. Integers. Integers are possible, but we can't have negative people at a meeting. So we don't want integers. So what about whole numbers? Well, we could have 0 people at a meeting. If, let's say, someone called the meeting, but there was traffic, they didn't show up, and no one else did show up either, 0 people could be at that meeting. So, yes, our domain that could be reasonable could be all integers. All whole numbers. We said not integers, whole numbers. All whole numbers. Okay, B, assume there are more than 15 people. Write an algebraic sentence using x. All right, well, so more than 15, 15 is not included, so x is greater than 15. All right, type C here, again, we're using integers. So, on our number line, we're going to mark the integers that are greater than 15. So that's 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Make our arrow, color it in. Pretty easy. All right, here's an example for you to try. It says, Charles used cars sold from 24 to 30 cars each week last month. Let n be the number of cars sold. If the domain of n, write an inequality to describe n and graph the solution set to part B. So pause the video, see if you can do this, and then come back and see if you got the answer correct. So, A says give the domain of n. So, the domain of n, well, let's see here. Real numbers. You can't sell a decimal of a car, so no. Integers. Can't sell negative cars. So, the domain is all whole numbers. All right. B, write an inequality to describe n. All right, so they sold between 20 and 30 each week, so we're just looking for the number they sold per week. So, let's see here. They start, the lowest they could have sold is 24. They did sell in. The highest they could have sold is 30. So that means n has to be less than or equal to 30. Now, let's see here. 24. So n has to be then greater than or equal to 24. So 24 has to be less than or equal to n. All right. So graph that. We said whole numbers between 24 and 30, including 24 and 30. So we put dots at here. 25, 26, 27, 28, 29, and 30. And that's it. No more. No arrows, just that. All right, let's look at another example. So let W equal the weight of a meat roast. Give a reasonable domain for W. The roast weighs less than 6 pounds. Write that as an inequality using W. And graph the solution set to part B. So reasonable domain. So let's just, again, go through all of our options. Let's start with real numbers. Well, that's definitely possible. You could have a decimal weight, 0.1 pounds. Now let's think about the lowest number that could be then. Since we know real numbers could be, let's say the lowest number. Well, it can't be 0. That would mean there's no roast at all. There is a roast. It exists. So it has to be greater than 0. But that's it. That's the only restriction there. So A, we could say real numbers greater than 0. All right. B, the roast weighs less than 6 pounds. Okay, so we already said the lowest it can weigh is not 0, but close to 0. The roast weighs somewhere between 0 and 6. So it has to be less than 6, and it has to be greater than 0, so 0 is less than W. Okay, so now we graph it on our number line. So you remember from the one earlier, when we did this, we said that when we had the less than symbol and not equal, we use a circle, an open circle. And when we're talking about real numbers, we do include it. So we're going to have an open circle. And use a different color. I thought I had one set, but I didn't. Right. Open circle. Me. Open circle on 0. Open circle on 0. Let's just move our number line to fit that there. Good. Open circle on 0. Then our second open circle. See what I'll do? I'll just draw an open circle. And that open circle will go on 6. And then we draw a line between the two. So it's an open circle with a line between the two of them on each end. And that's the solution set. All right, one for you to try. It says in the Beaufort scale, a force 11 wind is called a storm. Force 11 winds include winds of 64 to 75 miles per hour, which are strong enough to cause widespread damage. Let S equal to wind speed. Give a reasonable domain for S. Write an inequality to describe the possible speeds of a force 11 wind. and graph the solution set to part B. So, pause the video and try it yourself, and then come back and see if you get it right. Okay, so A says give a reasonable domain for S. So, well, S is wind speed. We can measure speed in decimals. We also can have no wind. No wind could easily exist. We can't have negative wind. So, we can use real numbers to describe this. Numbers. Greater than or equal to 0. All right, B. Write an inequality to describe the possible speeds of a force 11 wind. Well, force 11 is between 64, and we have our speed somewhere in between, and 75. All right, it's less than, but could be equal to 75. And it's greater than or could be equal to 64, so 64 therefore is less than or equal to S. All right, pretty simple there. And I will quickly show you the solution for part C. As you can see there, it just popped up. Big circle, closed circle on 64, closed circle on 75, and all the numbers in between are filled in with a line, solid line. All right, so something about intervals. Intervals are a set of numbers between two numbers, A and B, possibly including A or B, both, or both A and B. The numbers A and B are called the endpoints. An open interval doesn't include the endpoints, and a closed interval does. And if it has one but not the other, it's neither. So let's look at some examples here. Here's an open interval, again, doesn't include the endpoints. Closed interval includes the endpoints. And neither open nor closed, one endpoint but not the other. Pretty simple there. So that's all for this lesson. If you're following along, try problems 1 through 25. And I hope you enjoyed this video. I hope it was helpful. And as always, keep learning.